Hello, this is Postgres FM, and it's Michael. Hi, Michael.
Hello, Nikolay.
Oh, and my name is Nikolay, right? So, do you remember the number? Episode
Episode
number
68, I believe now.
68. Oh, yeah, great. And the topic today will be I chose it, and it will be over indexing. Next time we will talk about under indexing, I promise. Right?
Well, yeah, I mean, this is the age-old thing. You did a tweet series about over-indexing, and this is definitely kind of one big category of issue where both of us have come across people that have added a lot of indexes to certain tables, and that's caused a certain category of issue. But I'd actually say that in the majority of cases that I see that people have performance issues, it tends to be under indexing that's the problem for their cases. But yeah, maybe a whole nother topic for a whole nother day.
Right. Well, right. If you start without indexes, just with primary key, maybe even without it, right? Then you find out that indexes is a good thing. They didn't teach you when you learned SQL standard about indexes because they don't talk about it at all. But then you discover them, and so we have phases here. Phase one, you discover indexes and understand that lack of indexes hurts your performance, your database performance. But once you discover indexing, I bet you tend to do what we will discuss today. You create indexes too much. The silliest approach is to index every column, right?
Well, and worse, right? Because I often give that example and I forget that it's not even only as bad as that, because we are often, if you want to, let's say we're trying to optimize a specific query, often the optimal index is a multi-column index to help us get exactly the right conditions and get an index-only scan. And once you introduce multi-column indexes, it's not even just an index per column, it's an index per combination of columns in a specific order. So the number of possible indexes, even if we don't start to consider duplicates and overlapping ones, it is not even just the number of columns, right? It's way higher.
In general case, the optimal index is multi-column involving some expressions instead of columns, and also partial.
Yeah, yeah, of course.
Yeah. Well, okay. So nobody says we always need just one index per table. No, that's not so. Of course, we need multiple indexes. But what I'm trying to state is that having too many indexes hurts not only write statements but also reading statements, selects. By the way, my tweet, it's just one tweet. It's not a series. Series is Postgres Marathon, which is about everything, not only performance, all things Postgres as well, and just with some practical examples. But in this case, so many people, when they pass this phase one, lack of indexes, and they are in phase two, over-indexed, they realize, and it's discussed a lot, that indexes hurt. Too many indexes, extra index will slightly slow down write statements. And by the way, I made a mistake in my tweet saying that deletes are affected. This is my usual mistake. I think I made it during our podcast at some time as well. Deletes are not affected. Deletes just put xmax column value to tuple header, and they don't change indexes. So deletes are fine. Affected statements, write statements, are inserts and updates. For updates, there is optimization technique called HOT, heap only tuples update, which sometimes works, sometimes not, depending on a couple of important conditions. But my statement is selects are also slowed down, and we can discuss things step by step. Let's talk about writes first, right? So again, inserts and updates. Why are they slowed down? Because when Postgres creates new tuple, and each insert, each delete will create new tuple, even if you roll back the operation. If you roll back operation, they will be dead. New tuple will be dead, right? And when a new tuple is created, index entry has to be created in all indexes. It's called index right amplification problem in
Yep.
Postgres. One of the reasons Uber moved back to
Yep.
MySQL, very infamous story, right? And for inserts, there is nothing you can do because we do need to put additional pointer to each index. But for updates, there is hot updates, heap-only tuples. Two conditions needed to be met. First is there should be additional extra space in the same page as old tuple. And second condition, you should not change values for in columns which are participating in index definition, and it can be even where clause if it's a partial index. So, and for the basic example here is if you have updated add column. And by the way, Jeremy Schneider from AWS RDS team mentioned it in the thread on Twitter as well. So if you have updated add column, many people tend to have it, and then you have an index on it. Of course, when you change data, you change updated add value, but since it's an index, you never will have hot update for such updates. It's impossible. So idea is maybe you should not index it. Try to avoid it. But we might want it because probably we want like last 25 updated rows or something, right? So let's discuss this. What's the best approach here? You have updated add column, you update which maybe by trigger, for example, each update changes this value. But what to do? I want fast updates. I want hot updates. So tuple is in the same page.
This is one of the things I love about performance, that you just get hit with these trade-offs, and it's going to depend on your case, right? What's more important to you for that table, and what are you most limited by? What's your most precious resource in this case? So I don't think there's a generic. I think people try and give generic advice. I've definitely tried to do it in the past as well. And sometimes it feels like you can get like an 80-20 rule. This one feels like it very much, I know it's a bit of a cliche now, but it really does depend, right?
Right. Well, but how? Like, let's slightly discuss how it depends. First of all, I forgot to mention hot updates. It's when you I explained conditions, but what is hot update? Hot update it's when during update Postgres doesn't need to touch all indexes. So because if you have 20 indexes, it's hard to touch them. It's expensive and slows down update.
And this is because the tuple in the heap doesn't move page, right?
It's on the same page,
and we get I can't remember the wording for it, but it's like a little bit of extra information gets added to that. So it's like a link.
Additional jump inside page, right? So index keeps the pointer to the same page, same buffer, basically. And when we read something, we need to read whole 88 kibibytes block buffer page. And inside it, old tuple now says there is new version. It's super fast to just jump to new version inside it.
And the space on the page thing is important as well, because if you want to optimize for heap-only tuple updates, tables by default have a fill factor of 100%, don't they? But we can reduce that.
Artificial bloat. Right.
Yeah, but if we reduce that to something a little bit, giving a little bit of space by default on each page, yeah, sure. First, our table takes up more space, but in future we might be able to get that net benefit of our heap-only tuple updates.
Right, or just here we just can benefit from slight bloat we have, because if some space is left after some tuple became dead and then cleaned up by auto vacuum. This is how I'm sure most times in the world when hot update is executed, it was in tables with fill factor being default 100.
Yeah, probably.
It's just working because auto vacuum already cleaned up some old dead tuples. Right. So okay, and in this case, we of course, if we have updated add column, we need to decide if the index scan on if we have index on that column, and we use it. We rely on it a lot in our queries. For example, give me 25 lastly updated rows. In this case, probably we want to keep this index, but we understand that updating updated at will lead to degradation of this, right? But of course, like we also need to see the full picture here. If when we updated at column, change it. When we change other columns, maybe we already lost hotness feature of our update, right? Because we anyway change something which is indexed. Right. So, but in some cases, I saw like, and I recommended let's just get rid of this index on updated at. Our updates become very fast because we have too many indexes on this table, right? We need to update all of them. In this case, we have, for example, we have some payload which is, I don't know, like some JSON, and it's not indexed. We change something there, and automatically we change updated at. In this case, if we don't have index on these columns, neither of them have index. In this case, update is very fast, but how to find recently updated rows? I remember I wrote it a couple of times, relying on the index, so either on ID if it's sequential number, or on created at column, which is like default now, right, current timestamp, trying to find like lossy search, like you find more, and then if it's not enough, you get next. You search by created at, but you try to find updated at. It was some for maintenance, some approach. I just wanted to. I knew I don't want index on updated at, so I tried to find workaround. It's an interesting like engineering task, but of course it depends on the case you have. But it's worth keeping in mind. Such updates are quite slow. Right.
Yeah.
So, and speaking of inserts, probably you just want to insert in batches if you can, because in this case, many tuples will go to the same page, and it will be faster compared to single row inserts in separate transactions, right? So in this case, it might be faster. So, yeah, okay. What?
Oh, we've got. Is there anything else you wanted to talk about? So we've got the right amplification problem.
Right.
We've got hot updates, not only hot updates that can help alleviate that, but also it's another problem of over indexing, right? If we've indexed loads columns that we don't ultimately need, we prevent those. So there's both sides of that argument. And then is there anything else you want to talk about on those before we moved on to things
Of
like
course, we had an episode about index maintenance. So the easiest way to improve the performance of write operations, excluding deletes, I will never forget anymore. You need just to perform index maintenance regularly, like once per few months. You check all unused indexes and redundant indexes you have by far, and just remove them.
Yeah. So by unused indexes, we're using I've written it down here. Is it PG stat user indexes?
Right.
And not just on the primary. Ideally, if you're using read replicas, also on read replicas.
If you have multiple setups, check multiple setups, because there are difficult situations. For example, some software you install to users, like to customers.
Oh yeah, like a multi-tenant thing.
Not multi-tenant, the opposite. Multi-tenant is we have one database and many.
Oh sure.
Or if multi-tenant also interesting. If you have multiple databases, probably you need, or multiple tables, the same structure. It happens sometimes. You need to check them all to understand the pattern. Maybe not of them all, like maybe just like 10% to understand the structure. But I'm talking about when you install software, like for example, GitLab, you install it, customers install it, and who knows, maybe you checked several cases, index is not used, but who knows, maybe like 5% of your customers need this index. And also time matters. You need to check long duration of usage. We mentioned example when some index is needed a lot, but on the first day of each month. If you happened to check usage, result statistics in the middle of month and checked in the end of month, you might not see the pattern well enough. So checking usage requires some understanding as well, and it should be done carefully.
Yeah.
Redundant indexes also, like, some people have fears that if some redundant index looks like redundant, and we know like index on column A is redundant if with is an index on column A and B. So our A is on the first place, so we consider this index as redundant. But what if it's used? It can be used because it's smaller and the planner thinks cost is lower. It's
Oh
some people.
yeah, it will likely be used because it is smaller, right?
Right.
But it does. Yeah, you're right. Good point.
Like
So
you can
redundant
drop
can
it.
even be. Well, so redundant can be these overlapping ones like you described, but it can also be literal duplicates. Like Postgres doesn't
Oh
stop.
yeah,
It
duplicated.
doesn't. Yeah. So Postgres doesn't stop you. I think that surprises people. It doesn't stop you creating the exact same index definition as many times as you want.
Yeah, why not? So yeah, so just try to achieve the minimal set of indexes you really need. This is the general advice here. But let's
Yep.
move on to more interesting and
Well,
topics which are not usually discussed. Yeah.
I had like one, at least one more kind of easy one that we probably don't need to discuss much, but I think people often forget that they're competing for space in the cache as well. Like if you're in a position where you don't have, or your working set doesn't easily fit in memory, the more indexes you're creating, the more competition there is for that limited resource.
Right.
And then the final point was you mentioned index maintenance from this perspective, but it's also a point if you need to rebuild everything. If you like, for example, there was the issue in 14 that was fixed, I think, in 14.4. We needed to rebuild all our indexes. The more indexes you have, the longer that takes. Like there's a few things where the more you have, the more maintenance there is to do.
Yeah, exactly. Indexes health degrades over time, and you're talking about the case when like we rebuild index with concurrently option, either create index concurrently or reindex concurrently, and during this X-min horizon is being held, and after vacuum cannot
Yep.
delete freshly dead tuples, and optimization was attempted in 14.0, but all versions between 14.0 and 14.3 they have bug in this feature, and so fixed in 14.4. Yes, and yeah, so you're right. We didn't mention basic overhead from extra indexes. It's disk space and also buffer pool usage.
Yep. Good
Space,
point on disk space. Yeah.
and actually space in the page cache as well. So in memory.
Mhm.
So
Yep.
the more indexes you have, the more memory you need to maintain. Postgres needs to maintain them during operations, even if you don't use them. They need to be updated, so they need to be loaded to the buffer pool to be updated, and it's not good.
Yeah.
But let's talk about even more like interesting. Like I mean like what this tweet discovers and talks about. Probably it's not super big problem, but it's a surprise to many. We have a small table or bigger table. We use pgbench accounts, and I mean pgbench regular pgbench
Mm-hmm.
with scale like 100. It means like I don't remember the 10 million rows or so, like small table. And we just have, by default we have only one index which is primary key on this table, and we just check the performance of primary key lookup. It's simple. Select only workload pgbench provides by default with option dash capital hyphen capital S. Selects only. So, and then we just check performance, check planning time, check execution time, and then we add one more index. Right? And we see that performance of planning time degrades. And it degrades noticeably. Like first degradation is like more than 10%, 16% maybe or so. Like if you check even planning time only, right? Execution time doesn't degrade, but planning time degrades. And then one more index also like 9% or so. And then more and more. And then the speed of degradation goes down a little bit, like to 5%, but each index adds a penalty to planning time, 5% or so. It's significant. I mean, like it doubles very quickly by I don't know, like by index number
I think
8,
9. I'm looking at
9, 10, or
indexes.
something.
Yeah.
Yeah, right. So having 10 indexes compared to one index is like twice longer planning time, maybe even 7, I don't know. By the end, we reached 20 indexes, and the degradation was more than 4x, so more than 300% was added to planning time. But there was additional effect at some point. We will talk about it slightly later. It's even more interesting. But this is like super basic. Like index means more planning time to basic queries like primary key lookup. And why is it so? It's because the planner needs to analyze more options for more plan options, right? Obviously. And
Is this, just to check, are we adding the equivalent duplicate indexes on the primary key column? So it basically has a choice of
right,
all 16 or all 20 of the indexes. So
right.
it has to choose which one is likely to be the lowest cost.
Right. So yeah, this exactly shows also how bad it's bad to have too many indexes, especially duplicate indexes or unused indexes, even for selects. But it affects only the planning time. Uh, this overhead affects only planning time. And of course, if you can get rid of planning time for most of your queries if you use prepared statements, and it's easy to check with the same pgbench saying dash capital M prepared, and you will see there is no effect. Like you can add as many indexes as you have, and planning time is very small because there is no planning time for most queries. It's planned only once, and then it's reused, the same plan. Right. So and yeah, it's worth saying that this Monday, this week, pgbench finally, like I waited, like honestly waited, not
PG Bouncer.
pgbouncer, sorry, not pgbench is for benchmarks. Yeah, pgbouncer, which is still the most popular, I think, puller,
Yeah.
right? Although there is competition growing last years. Finally, pgbouncer got support of prepared statements for transaction pool mode. Transaction pool mode is the most interesting because it like has most benefits. We discussed pullers as well in our another
Yeah.
episode, and people who were using pgbouncer, a lot of people, could not use prepared statements, and now they can since this Monday, and this is a big feature, and I'm glad that it happened finally. So I mean, I wanted to say maybe not 15 years, but close to it. I waited for it. Like Skype released pgbouncer maybe in 2007, 8 or something, like almost 15 years definitely. So I didn't want it like too much, but I obviously observed a lot of projects who would benefit from having this feature. So it's great that it was released, definitely. And
How are you going to celebrate?
benchmarking.
Seems appropriate.
already
Yeah.
benchmark party, you know.
Yeah.
So yeah, I wanted to thank all people who involved into this.
Yeah.
So, yeah, I don't remember all names, but I want to mention a couple of them. Jelte Finema Neil, sorry if I'm pronouncing it wrong, from Microsoft team, and also Konstantin Knizhnik, who created the latest version of the patch this spring, I think, from the Neon team, and a couple of more folks who prototyped in this direction. And I forgot names, sorry, but obviously it's like multiple teams, multiple people and teams actually were involved, and it's great to see that it's released. Knowing the history of pgbouncer development, I actually expected that this patch won't be merged quite soon. So that's why I said it's super fast. It's not fast. Yeah, Jelton mentioned that it was like 1.5, like 1.5 years of work. But from perspective of 15 years of waiting. So anyway, good news. Each index adds penalty to planning time. It's probably very low, sub-millisecond for small cases, but it might be already like millisecond, depends. For primary key lookups, which are very frequent, for example, thousands per second, it's a lot of CPU time. And now, if you use PG Bouncer before this Monday, you could not use it. Now you just need to switch to prepared statements and enjoy that CPU goes down at least a little bit, right? And primary key lookups will be much faster now. Give me your skeptical opinion about optimization on sub-millisecond timing.
Yeah, well, firstly, I commend anybody that actually looks into this stuff and benchmarks it and shares the data. I think that's a step that people often miss when they're talking about generic advice around this. I saw the numbers shared around. I think it's dangerous, isn't it? Like, you share data and then people quote it without looking into it themselves. So even the PG Bouncer stuff, they ran some synthetic workloads and showed it was between 15% 1.5 to 250% faster, depending very much on the synthetic workload used. And I've seen some people then quote that saying it's minimum 15% improvement to all workloads. Yep. It's like, that's not what it means.
Right.
So I think it's it is a bit dangerous to say that without checking for yourself. Like, do testing and do your own research. But so that's kind of where I want to go with this degradation of query planning time. The graph that you've done is great, but the y-axis is only, like, even at the 400% degraded query planning time, we're talking about a total of 0.1 milliseconds on average planning time.
Right. First of all, it's not a mistake in that tweet. I'm fixing it in the final repository of these how-tos. Nice. These problems will be solved. I hate when people, in this case, it was not people, it was ChatGPT who wrote this graph with this advanced data analysis. It was a bunch of Python. If you say don't do it, it won't do it anymore. So you shouldn't start y-axis not from zero, right? It should be always from zero, right?
I agree generally, but I wasn't even talking about that. I was talking about the other end of the y-axis. Like, what's the maximum average planning time, even at 20 indexes here?
Let me explain from this point of view. For most quite heavy queries, the planning time is like the smallest fraction of everything, right? So
yeah,
and optimization, if you even if you go to zero planning time, probably won't be very noticeable. But that's why I keep talking about primary key lookups or other index scans or index only scans when we have execution time is very small. And planning time compared to execution time, it becomes noticeable, sometimes exceeding it. And in our, like, if you have a table and create 20 indexes, in our case, we showed that planning time is already 4 times more than execution time. It's 80%. And if you remove it from the picture, it's 5x improvement. Of course, we still talk about like sub-millisecond queries, but if you have 10,000 of them per second, it's significant, right?
Yeah. I completely agree. And I'm a big fan of this. Even in your example, you show that even with only one index, planning time is about double execution time. So we're talking about significant planning time here, regardless of how many indexes there are, if you're looking at it in relative terms. I'm just saying, for people that want to hear these numbers, check for yourself on your own data as well, because we're talking about 0.1, like you say, sub-millisecond, but it's not even that. It's sub a tenth of a millisecond. It's like another order of magnitude.
Yeah. Of course, it's because in our case, this case was a very small table. Again, 10 million rows. Yeah. It's not nothing. 10 million rows. These days it's small.
So on to more like specific things. I would be interested. I don't see many people, like, I do see some duplicate indexes, but what's the same effect of having 20 indexes when they're not all on the primary key? Like, my understanding is that this affected planning time because the planner had to consider
different. That's a good question. We should check.
But so again, like, most people don't have that kind of, I've got 20 indexes on the table. They don't have them all on the primary key.
Good question. We will double check this path as well. like indexing different column, which like for planner, it should be obvious that checking those indexes doesn't matter.
Yeah.
Doesn't make sense. Doesn't make sense. But who knows if planner has this optimization? Let's check. I wanted to say there's another test Vitaly Kuharik created yesterday, actually, checking this new feature in Page Bouncer, and CPU load was like just again moving from 1 index to 20 index. And with prepared statements, through Page Bouncer, everything, CPU load went from 80% to 40%, so 2 times less.
Wow, nice.
Just switching to prepared through Page Bouncer. So this is like, but again, it's very specific case, primary key lookups, indexes, extra indexes on the same column. A real case can be very, very different from it.
Yeah. And then one more thing that you don't, in fact, we should discuss here that where the graph changes shape a little bit. But before we do, another thing I've realized we haven't talked about is a case that does hit people pretty hard, which is too many indexes plus partitioning with dodgy lookups.
Let's switch to final topic, which is like should be like a cherry on the top of this cake.
Yeah.
When you reach, like for this particular case, simple query, one table, primary key lookup, you just add extra indexes. No other tables are involved. The thing is that when you reach index 15 and add index number 16, degradation is much worse. But only if you have multiple session experiment. I mean, if just one session, you won't notice it probably. But in concurrent environment, when many sessions run this primary key lookup, when you add index number 16 and number of tables and indexes altogether exceed 16, this threshold hard-coded in source code. In this case, you start observing additional degradation from log manager behavior and it can be observed as wait event lightweight log. Wait event type is light LW log, and the wait event itself is called log manager. So log manager starts doing some additional work because the thing is that when you just run some select, this select is going to acquire a log on the table and all its indexes, even if they don't participate in the plan at all. Like you don't need them, but still Postgres needs to acquire access share log to block possible DDL, basically, right? So and it will be released only at the end of transaction. So to acquire a log manager needs to deal with memory. So there are slots basically, and when it's doing it needs this lightweight log. So your select transactions, start competing for this log acquisition. I mean, they're not blocking each other, but acquisition takes some time additional. Why it's 16? Before that, there is a thing called fast path, and there is another algorithm which is not full-fledged checking. It's faster, but once you need more than 16 access share log, this is the lowest heavy log. Access share
and
log.
Is this like a hard-coded number, or where's this 16 coming from?
It's a hard-coded number. It's called FP log slots per backend. Fastpath log slots per backend is 16, quite old thing, and that's it. So even if you have 100 or more vCPUs, terabyte of memory, this hard-coded number can hit you badly. Mm-hmm. And why I switched to this topic, because partitioning can be involved here, because partitioning is multiplier of a problem. If you, for example, have a simple selects to some table and you have 15 indexes, relation means in Postgres terminology, relation is both tables and indexes. It's called relation. So table plus 15 indexes, it's 16 relations. All logs will be fast path. By the way, a comment on it might look surprising that we need to log all indexes even if they don't need them.
Yeah.
It's so. But it's so, yeah. But I'm curious if it would be implemented differently, like virtual locking for indexes. If table, like indexes do not live without tables. If table is locked, we could consider indexes also locked, like it's additional check in some pieces of code, but maybe the checking this is less problem than dealing with this fast path versus not fast path.
Good question.
Oh, by the way, fast path can be seen by hands. You just select from PG logs, and there is a column called fast path. But when you're checking this, you need to do it in another session, knowing PID, process ID of your main session. You just don't close transaction. If you just say begin, select something, and keep transaction open, and then from different session you look at PG logs, knowing the process ID of the first session, and you will see all the logs. You will see relation level logs, heavy logs, and you will see which of them fast path, which are not, and fast path is 16 maximum. So this is hard coded, and there is a discussion on Hacker News. I think there are several discussions. The latest one I started, and originally it was like maybe no, but now Thomas Vondra proposed some patches. We are going to explore them. So to increase this threshold to 64, for example, or yeah, there are complexities.
Did you say Hacker News, or do you mean Hacker's mailing list?
Sorry. Yes. Hackers.
Yeah. Okay. That makes. I was thinking.
No. Such things are not discussed on Hacker News.
For a Hacker News discussion.
Sorry. Mixing terms here.
That makes way more sense. Let's link them up. I'll do that.
PG Bench versus PG Bouncer and Hacker News versus PG Skill Hackers. Of course, yeah. sounds similar. Sorry for mess. So there are proposed patches, and to raise this threshold, and it turned out it's not so simple as I thought originally. Like one line, like you just change to 64. No. There is a big discussion of complexities of this move, and I think it will be great to move this forward, and I plan to test it. But back to like how it feels. I see several cases when it was very bad situation when this lightweight lock wait event came, and many sessions are starting to clashing on this, right? And we quickly reach a number of active sessions, like reaching number of CPUs we have, vCPUs we have, cores we have, and exceeding it, and it puts server on knees. I mean, we have brief outage like lasting from several seconds to maybe a minute. It's a bad problem actually, and it's also a hard problem to understand. But the main how it looks like, you see this lightweight lock manager in wait events. So unfortunately, there is nothing you can do here except reducing number of relations. For example, removing some indexes or reducing frequency. It happens when frequency is high. If frequency is low, you won't notice. You can have 100 indexes, and they will not there is no contention observed. But if you have many indexes, and for example you partitioned, and some queries don't have partition pruning involved in plans, meaning that they need to deal with multiple partitions, maybe in worst case all of them, and each partition has, for example, 15 indexes. Obviously you have a lot of non-fast path locking involved, and it slows down lock manager behavior, and you see this spike of lightweight lock manager lock contention.
Yeah, well, and it can be even fewer indexes can be a problem. As soon as you've got, let's say, like 10 partitions, and you've forgotten that you have
partitions, right?
Or even like 2 indexes. Yeah, it becomes an issue really quickly. And I think this is one of those like confounding factors where it's not even an issue of too many indexes. The main issue is you've forgotten a couple of queries that don't have the partition key in there, like a couple of frequent queries that don't have the partition key in
they should be frequent. If they're not frequent, it's okay. I mean,
exactly. And it's that, and then that hits this issue, and then that kind of cascades into other issues. So yeah, a really good point about this. I think this is really
right.
important.
So partitioning, but in general, when partition pruning in plans is involved, at least in Postgres 14 and higher, if you deal with plan is working only with single partition, you won't see logs for other partitions. I just double check manually for safety.
Yeah.
It's so I checked it a couple of days ago additionally. So it means that you can have 10 indexes and work. By the way, if you join with other tables, again more indexes and like joins also multiply this problem, right? So if you like, I'm talking about high frequency queries, like thousands of per second, and the lack of CPU power we have here. Because if you talk about 500 per second and you have 128 vCPUs or 244 with like modern AMD EPIC, for example, generation 3, right? In this case, probably you won't notice this problem. But if you start noticing, and it can be noticed early stage, you just see wait events popping up. You don't have outage yet, but already these wait events, you should be very careful. Consider index optimization, reduce indexes, check the plans, try to reduce frequency, and what else? If it's primary key lookups, back to our situation with planning time. If you see planning time is significant here, it's time to consider again, if you have page bouncer, to consider prepare statements and reduce this like duration these logs are being held, because they are released only at the end of transaction. Yep. So
nice.
Right. So yeah, this is probably, by the way, one of the biggest performance problems Postgres has right now, which is hard coded. Probably it will be improved, and of course only projects with high frequency queries experience it. But it's an interesting problem. I consider it as similar as subtransaction issues I studied like a few years ago. So yeah. Oh, by the way, also worth noting that the RDS documentation has very good wait event pages.
Documentation.
Like for like most popular wait events, they have a whole page. It's much better than official documentation because it talks also about use cases, what to do, how to diagnose, and so on. And for this particular lightweight log manager, they have very good page as well. So worth checking it.
I'll put it in the show notes.
Good. So that's it, I guess, right? So like, don't allow over-indexing. Under-indexing, it's next time.
Yeah, probably most of you listening are still in the under. I would guess most of you are in the under-index stage, but the ones that are in the over-indexed, I'm sure this would be.
We should have a vote somehow. Like, do you feel over-indexed or under-indexed? I can do it on my Twitter and LinkedIn.
Yeah, great.
Yeah. Okay, good. Thank you, all listeners.
Yeah, thanks so much, Nikolay.
Yeah,
as
usual, if you reach this point, it's definitely like we ask you to share it with your colleagues or friends who use Postgres, and also we also ask you to provide us some feedback and ideas for future topics. Right? Maybe there are no many topics left. What's your feeling here? We covered everything already, right? No?
Yeah, I'm finding the more topics we do, the more research I have to do for each one. We're getting to the ones where either one of us knows it. Like, well, actually, this is a bad example because you've done like, part of this research as part of your work anyway. And yeah, I think we're having to dive deeper for each new topic now, or we're having to cover ones that we're less familiar with. So yeah. But I don't think we're near running out.
Best Postgres library, best Go library for working with Postgres. There are interesting nuances there. So
honestly, and we've only if you look at the index types, we've talked a lot about feature indexes mostly today. I think we did one on Brin indexes, but we've never touched. I don't think we've done one on
fast update.
Don't think so. Well, I think we mentioned it, but not. Hash we haven't talked about.
Okay, we have some fuel. Don't write us. Okay. Okay.
Take care, everyone.
Thank you. Bye.
Bye.